Hi, it's Patrick with the E38. In this video, we're going to go through a full workflow running a mission with the DJI Zenmuse L2. All the equipment used in this video is available at e38surveysolutions.com and consists of the L2, DJI RC Plus, DJI Matrice 300, and the Emlid Reach RS2 base rover essentials kit. We also have ready-made bundles with more or less equipment included to suit your needs. Now let's get started. Since we're going to set up our base over a known point, I'm going to log into Emlid Flow 360 through a web browser, create the project that will contain our Checkshots, and manually add our known point for the base to use. Check out our Opus S beta video to see how we acquired these coordinates. Out in the field, we'll set and level the base, boot it up, and make sure the settings and configuration are correct. I want the base output to be over the lower radio, so the rover will receive corrections while I collect my check shots. I'm going to check on my logging settings and make sure I'm recording the necessary data for post-processing the L2 data. Since I'm connected over Bluetooth, the RS2 wants to establish a Wi-Fi connection to adjust these settings. Emlid Flow will facilitate that without having to go into my phone's Wi-Fi settings. It looks like the receiver is using the default for logging in Rhinex 3.03, which is fine. I'm going to turn on auto start and backup source data for Rhinex. So when I tap apply and restart, the next log, which will be what I use for the LiDAR data, will start then. The last thing to do for this step is to import the known point for the base by changing the coordinate entry method to manual, inputting the pole height, then selecting choose from project, and selecting the known point. Over on the RS3 rover, it looks like I'm already receiving corrections and have a fix. On the survey screen, the pole height looks to be correct on my rover, and I'll be averaging each shot for 5 seconds. I've turned off tilt compensation. That will eliminate the additional error of 2 millimeters plus 0.3 millimeters per degree of tilt on top of the existing RTK error to get the most accurate check shots out of the equipment. I'm going to use high contrast points for my check shots. You can paint 1 meter by 1 meter black and white targets, which is what DJI recommends, or you can use reusable GCP targets or other high visibility paint targets, or you can use existing high contrast paint like zebra crossings, or in this case, I'm shooting the corners of parking lot spaces. I have a relatively small data set, so I'm only going to collect 4 shots across a good chunk of the LiDAR data. It's also good practice to get a few check shots under tree canopy to check the accuracy of some of your areas with multiple returns. Now that I have the check shots, I'm going to set up the Matrice 300 with the L2 payload and plan the flight. Everything else here looks good, so we'll upload and start the mission. During flight, we have multiple views available to us. We can look through the RGB camera or take a live look at the LiDAR collection, as well as having them side by side. Also, we can view the first person view from the forward positioning camera or the map view of our mission in progress. The back and forth motion is the IMU calibration, highlighted in the yellow on the map view. At the top of the screen, we have our flight mode, satellite count, and RTK status, as well as the RC reception and battery levels, and an estimated remaining flight time for our batteries, stretching from left to right across the top. At the bottom of the screen, we can tap the additional views to open them or press one of the soft keys to switch to the labeled view. New to the L2, we can view a pre-processed LiDAR point cloud. Now that our flight is complete, we can power down everything and head to our PC for processing. I'm going to start by downloading my base's log for the mission. Since my RS2 Plus has the office Wi-Fi saved, it will automatically connect to it on boot, and I can access it through a web browser to download the log file. A full tutorial on downloading logs is linked in the description. While that downloads, I'll remove the micro SD card from the L2 payload and connect that to my PC. With my base file downloaded, I'll unzip that file and have that ready to prep my L2 mission folder. I'll then copy the data from the L2 to my computer. I'll rename this mission folder so I don't confuse it with another. Then within the mission folder, I'm going to copy the file name of one of these files with identical names and paste that to the observation file in the Rhinex folder from my base. I'll also change the file extension from .230 to .obs and put that in the mission folder. I'm going to download my Checkshots from Flow 360, and then we'll have everything we need to process and check our point cloud. I just need to open the project with our Checkshots. Flow 360 will have already synced with Emlid Flow on our phone, so I can export the data by going up to and clicking export. I don't need all of the data available here, so I'm going to export a custom CSV file with just the name, easting, northing, and elevations from my shots. Now in Terra, I'm going to start a new LiDAR point cloud mission. We'll browse for and select the mission folder we just prepped. Then directly underneath our dataset, we'll click the settings for our base station. I'm then going to input the same known point we used for our base, except that I'll add the height of the rod that the receiver was on and save that. For the point cloud, I'm going to process it at 100% density. The density will mostly affect the time to process and shouldn't have much effect on the accuracy of the point cloud. Under point cloud processing, we have the option to optimize and smooth the point cloud, as well as add parameters to automatically classify ground points, generate a digital elevation model, and add contours. These automations work fairly well. However, we have more control in other software that we can export to, like LP360 or BricsCAD, to accomplish the same thing with better control to allow a better final model. So I'm not going to generate those here. In the advanced section, I'm going to select what coordinate system I'd like the point cloud to be exported in. Then click on Accuracy Control and Check. Here we can import our Checkshots from the CSV we exported from Flow 360. I'll define the columns. I'll need to select the coordinate system I used for the checks to bring these points in properly. And I'm also going to skip that first row that contains our headers, and then click Import. As you can see, it brought in my checks as ground control points. Leaving them like this will pull the point cloud to those elevations. Since the L2 is spec'd to be more accurate than our GNSS receivers, I'm going to change these to checkpoints to compare without affecting the point cloud. With our checkpoints in, I'll start the processing. Give it one more look through and everything looks good, so I'll click OK. The processing is complete. We can now take a first look at the processed LiDAR point cloud. I'm going to take a look at our accuracy compared to the checkpoints. Visually, we look to be close. We can check the hard numbers by clicking the quality report. We are looking pretty good. Our biggest outlier is the known point where our base was set up, which makes sense since Terra is averaging all the points in a small area and comparing that value to the checkpoint. There are a few other tools available to us within Terra. The cross-section tool lets us take slices of that data to see a profile view of the points and their values. We can also check individual coordinates, distances, areas, and volumes. I'm going to export this LAS and further process this data. Check back with us soon to see that. This has been Patrick with E38 Survey Solutions. Thanks for watching.